Right.
can see perfectly.
Great. So let's see. Let me make this smaller. Okay. So yeah, today I'll be talking about learning with less data. Specifically, we are going to look at data efficient methods using probabilistic machine learning. So yeah, in fact, this is the one of the key focus in our research group. And I have many collaborators with me, some former PhD students who have moved on to do PhD in CMU and Cambridge. I also have some former PhD students who are now at the MIT IBM AI Watson Lab. And I also have a very good collaborators from MIT and NUS Business School as well. So they have all been collaborating with me in some of these topics that I'll be talking about. Oops. Okay, now just to give you a rough overview of what kind of stuff we're doing for learning with less data. So on the left-hand side, what you do see is what I call active learning. The underlying issue is that you have an unknown function, right, that you want to learn. And the question is, how do we gather data samples, right, about this unknown function? In fact, we want samples that are as informative as possible, those that contains a lot of information about the function. And the hope is that we don't need to gather so much data samples, right? So that there are a few advantages. Firstly, if you are trying to train a model with less data and data that contains a lot of information, you can train, typically you can train the data in a shorter amount of time, right? Second advantage is when you collect less data and data costs money, right? For example, clinical data, you need people to anonymize it. Every time you anonymize, it costs something. So you want to extract or use anonymized data as few as possible, right? So that you can learn a model. Now, the hope is, of course, the data that you ask for, they contain a lot of information. This will allow you to build a model that's as accurate as models that are trained with all the data, right? For example. Now, it can also be applied to places like sensor placement, right? Where should you place your sensors to get the data with the most amount of information about the phenomenon, all right? So this is the first area that we have been working on. It's what we call active learning as opposed to passive learning, right? Passive learning is like, I throw you all the data and you just have to ingest them. You don't really have a choice. And active learning is in fact something that we as humans, we commonly do. We don't read everything under the sun. We study things that are meant for exams, things that are relevant, right? We actively select what to learn, all right? Now the next topic, which is the one on the right, which I'm going to elaborate on later on in my presentation. It's kind of similar to active learning. Remember I mentioned in active learning, we are gathering samples, highly informative samples, right, that help us to learn about an unknown function. Now on the right side, we don't just care about the unknown function, we specifically care about the optimum, right, the maximum or the minimum of the function. We want to gather data samples that help us to figure out what's the maximum or what's the minimum. Now, something like this is actually very useful in recent work on automated machine learning, specifically hyperparameter optimization of deep learning models. For example, how do I know how many layers we need? What's the learning rate for each hidden unit? How many hidden layers? How many hidden units, right? So in the past, for us, we often treat it like an art, right? We try to click a few layers, a few number of hidden units, and there we go. If the performance is not good, then we readjust accordingly. But these days, what we can use are tools like Bayesian Optimization to help us to optimize it. I'll elaborate more on this later, all right? Now, this is just an article that is available on my own website, right? You can find my website here, all right? It's an article on my website that describes a lay article, right, that describes what Bayesian optimization is about. You can imagine that, you know, you have your grandma who's trying to bake the best cookies, and what would be the optimal recipe, right, to such that it becomes the most tasty cookies to us, right? There are other interesting examples as well, or applications of Bayesian optimization. I'll talk about them later. Now, you will also see Bayesian optimization being used in AlphaGo, right? That's something that all of you know. It has been used to optimize the hyperparameters in AlphaGo, right? That's something that has been used. And in Google, they have been using Bayesian optimization as a standard toolbox that people have, right? Within the company itself, right? To help them out. Now, the last topic that we have focused on in the aspect of learning with less data, right? Earlier on, you saw that I'm learning about a function. I'm learning about the optimum of a function. Now, in this regard, when we talk about multi-party machine learning, it has the following scenario. I'm a certain party or a data owner. I don't have enough data to learn a good model. Then who else can I rely on? I can look at some partners, right, to collaborate with so that we can kind of build a common model or models or share data so that we can build or improve upon the model that we have, all right? Now, some of these topics that we have currently been looking at is the following. We ask ourselves, imagine that we have a self-interested data owners. In other words, every data owner has their own interest to improving their model, but they also know that if they are going to be able to incorporate the data or the modeling information from other parties, this will potentially improve their own model. However, bearing in mind that the data owners are self-interested, it would be great if they don't have to review their data source. It would be great if they don't have to review their model architecture, the model parameters, right? And it would also be great if I can collaborate with another data owner who possess a different machine learning model, right? So we have been looking at issues where what if different data owners or different modelers, they have pre-trained models that are black box to each other, means I don't know the model architecture nor parameters. The models could be heterogeneous, right? In other words, they can be different, right, across different owners. Now, how do you do fusion of such models, right, to get a better model? So we have some works in ICML 2019 and 20 on something like that, okay? You can imagine such models being deployed on autonomous vehicles next time, where all the vehicles are owned by different car manufacturers. They have their own proprietary model. Nobody's going to share their model with each other, right? So this will be useful. You can also imagine hospitals coming into the loop where they are not so comfortable with sharing the entire model of their own, but they don't mind if you can make it black box, right? Yeah. And the second question that we have been asking very recently is that how do we incentivize all these different data owners to share their data, right, to build models together? So this is something that I won't elaborate on, but we have a paper on trusted data sharing and data valuation in ICML 2020 as well, right? I can tell you more if there's time, all right? So moving forward, I'm going to focus on just one of the topic of the three that I've mentioned, specifically on Bayesian optimization, right? So like I've mentioned, we care about finding the global maximum of the function, but such a function is sufficiently complex and unknown. What do I mean by complex? It's not convex. More importantly, there's no closed form expression nor derivative information. And as a result, you can imagine gradient descent methods won't be useful here, all right? And very typically, in this community, we model such a unknown function as a Gaussian process model, which is a form of Bayesian non-parametric model, right? One of the key reasons why we want to model it as a Bayesian model, right, is that Bayesian models allow us to capture uncertainty, right? Uncertainty of the function surface. Now, the intuition is that in areas where you are highly uncertain because there's a data sparsity, you don't have enough data there, then you have a greater amount of uncertainty. As a result, you might want to sample there to learn more about the function, all right? So that's why Bayesian model is very useful in this regard, okay? Now, on the right side, I'm going to run this. I hope you can see the simulation, right? What you do, oops, sorry. Now, what you're going to see is that you're going to gather data samples about the function surface. This is the ground truth. The top left is the ground truth. Well, remember that it's unknown to us. And all these white spots are the ones where observations are being gathered in each round of the Bayesian optimization algorithm. Now, in each round, we are going to provide an input query, and they can provide to us what the output will be, right? So you can imagine that every time I provide an input, you give me an output, all right? Now, if you take a look at this top left, you're going to see that initially, remember that we care about the optimum, right? The optimum is somewhere here, right? Now, what you will see is that in the beginning, Bayesian optimization algorithms does this notion of exploration, right? What they do is that they try to explore the function surface enough to kind of know where are the optimum, or where are the local or global optimum, right? Potentially. And in the later stage, you'll see them exploiting. What that means is that after they spread sufficiently the observations throughout the surface, they will try to concentrate the sampling on areas with very high values, right? Those are the areas where potentially you will have the global optimum, all right? So this is the behavior of Bayesian optimization algorithm. Even though this is a mock setup of a very simplistic two-dimensional objective function, however, Bayesian optimization can actually be used in more realistic settings, specifically, like I mentioned earlier, hyperparameter optimization, right? Where people are using this tool to optimize the number of layers, hidden units, how many there are, what the learning rate would be, things like that, all right? Now, in recent years, what's interesting as well is that it can also be applied to other domains, right? And people have already started to look into this, right? For example, in the field of reinforcement learning, there is this branch of techniques called policy search. Bayesian optimization can actually be used to search for the optimal policy, all right? There's also other interest in, say, material science or material design. How do you fabricate a certain material, right? By optimizing the properties of that material. Now, in all these applications, what you do notice is that every time you sample, right, the function, just one, it's going to be costly either computationally or economically, right? For example, in hyperparameter optimization, what this means is that you provide the input hyperparameters, like how many layers there are, how many hidden units, and every time you train the neural network, it's going to take a very long time, hours to days, right? And you get the validation accuracy upon convergence, all right? And using that is just one data sample. Now, the key is that you want to find out what is the optimal network architecture that gives you the highest validation accuracy, all right? There are others as well. For example, in reinforcement learning, you're trying to figure out the optimal policy, right? Yes. So there are other problems like precision agriculture, where we are trying to figure out what would be the optimal environmental conditions to maximize my crop yield or vegetable yield per unit cost, all right? So you can imagine vegetables or crops, they take days to weeks to grow, right? It won't be immediate. As a result, it's either computationally, time, or economically costly, all right? So you can imagine as well that you want to gather as few samples as possible, all right? Now, in the next few slides, I'm going to show you different variants of Bayesian optimization algorithms that allows you to be more practical, all right? Now, the very first variant, which we have in UAI 2019, is what we call multi-fidelity Bayesian optimization. Now, the problem, maybe I describe the setup to you, right? First, now imagine that you want to train a CNN model using CIFAR-10 data set, 50,000 images, 3 hours to train per network architecture, right, on average. Now, every time you're going to try a different hyperparameter configuration, it takes 3 hours. But if the validation accuracy is not that good, you're going to try another new set, right? And this is going to be very expensive if you do that over many BO iterations. Now, the question is whether there's any way to speed this up. As an example, could there be some kind of auxiliary setup or auxiliary function, right, that allows us to sample more cheaply yet it provides some information about the target objective function that we have. Now in this setting, the target function is the validation accuracy for the CNN model on top. It's costly to evaluate because you need to train it every time with 50,000 images. On the other hand, suppose we want to train a CNN model where we only use 5,000 randomly sampled images. This would be much faster, say half an hour. But we do know that there's some relationship in terms of the validation accuracy between the two CNN models. However, we know that the one at the bottom is not going to represent the one on top with perfect fidelity, right? They're not, the one at the bottom is not perfectly replicating the one on top. So it has some degree of correlation, although not perfect, all right? Then the question is, do I spend more time to obtain more samples of the validation accuracies on top, or can I spend actually a lot more effort to sample the one at the bottom because it's so cheap, right? So I can actually do more iterations of it, right? How do I balance them, right? And as a result, allow us to reduce the amount of time to convergence. Now you can see on this plot on the right that the one in green is our method, right? It allows, using this method of exploiting auxiliary information that is cheap to evaluate, right? It allows us to achieve a better validation accuracy at with less time, right? In this case, it's about, say, 12 hours, as opposed to the next one that takes about 30 hours and beyond, all right? Now, what's also interesting is that we are using this piece of code in Keras, right? That by default gives you some hyperparameters to use. That's the one that's represented by the black line, all right? And you can clearly see that Bayesian optimization gives you a better performance than the one that you just use as default, okay? So this is the very first setup. Now the second one is what we call batch Bayesian optimization. We have published that in ICML 2017, right, with my former undergrad student. Now, what's interesting is that from the previous setup, you can see that every time I try to sample to obtain a validation accuracy point, it's doing it by one sample per iteration, right? Now, on the other hand, suppose you're doing hyperparameter optimization again, but you have multiple servers, right, to help you. Could I have asked each of this server to help me with a certain hyperparameter configuration to determine the validation accuracy? Now, of course, if you run the conventional BO solver on them, then all the servers are going to find the same hyperparameter configuration for you, which doesn't make sense. So in this case, we ask the question, how can we coordinate all these servers, right, to be able to jointly optimize the hyperparameter configuration so that no one server is kind of duplicating the same process as another server, right? No wasted effort or redundant effort, okay? Now, something like this would also be very useful in material design or precision agriculture, right? For example, in going back to the example about growing crops again, no farmer will just grow a single crop and see if it's going to grow well. Usually they will have a certain plot of land to try different settings, right? Of different configurations of environmental conditions. For example, on certain plots, they will use more minerals of a certain type as opposed to another, all right? Same goes for material fabrication, okay? Now, the next one is what I call high-dimensional Bayesian optimization. We have this work in AAAI 2018. So what happens is usually in optimization problem, one of the key aspect or key problem that people ask me is what is the input dimension that you can go up to, right, for us to optimize. Now, in this case, in our own group, we managed to reach up to 9,000 input dimensions. And to be able to do that, we exploited this additive structure of the objective function, right, to help us out, okay? So that's that. We have applied it to, for example, you can see on the right-hand side, where there are 77 toll booths or ERP entries for those in Singapore who knows, right? And we want to optimize the toll fee. to be able to improve the traffic flow. All right. Now in this next setup, we look at the following aspect. Previously, you have seen that, in BO or conventional BO, it is greedy in nature. What that means is that it's always going to ask what's the next input query to optimize, to sample, right? To get the corresponding function value. Now, however, what happens when you have an application where it allows you to look ahead? What that means is that if you're going to take the next sample, this sample influences the samples that you're going to get in the future. As an example, think about an autonomous vehicle, right? Think about an autonomous vehicle where it is trying to go to a hotspot, right? To pick up passengers, okay? Now, the road segment that is going to travel on next is going to determine the future road segments, right? That you will travel on, right? You can imagine exiting from a highway and trying to get back to the highway is going to take considerable effort, right? So in problems like this, it makes a lot of sense for us to look ahead, right? To be able to tell what happens if I take this next sample, how is it going to influence the data samples that I'll get in the future, all right? So in this work, we ask the question, if we look ahead, how much performance gain do we get, right? Out by looking ahead. Remember, of course, in our, as you know, you probably know, if you need to look ahead, probably you're going to need more computational effort, right, in order to look ahead. Okay. Now we exploit this notion of macro actions, which is something that is exploited or is taken from the reinforcement learning literature, specifically the model-based RL. All right. Now, in this next line of work, Bayesian optimization with early stopping, it is relevant to problems of the following nature. Now, remember, again, in Bayesian optimization, we are collecting data sample each. Now, specifically, say in hyperparameter optimization, remember that we need to train a model. But along the way, if you're using stochastic gradient descent, along the way, you can see that, hey, the model is not performing so well. At the end of the day, it's not going to reach a very high validation accuracy. Now, in this case, wouldn't it make more sense for us to stop it early, right? And save on some time. And that's one classic setting where this is very useful, right? Can we make use of early stopping in Bayesian optimization to stop those training where it is not going anywhere or it is underperforming, right? And as a result, we are allowed, or it is better off to stop them early, right? So another example again is about growing crops. You can see along the way, it takes a few weeks to grow, but along the way, you can see that the crops are not growing so well. Then we might as well, remove them and start growing a new batch all over again, all right? So this is something that we have done, and it allows us to improve the convergence, right, to the global optimum. And you can find this in our ICML 2019 paper and UAI 2019 paper as well. Now, in this year, in ICML 2020, which is going to happen in a week's time, right? We have two papers on Bayesian optimization. This first work is on Bayesian optimization with recursive reasoning. Again, I'm going to look at the example to help to motivate why we need this. In this case, we are talking about adversarial machine learning, right? Imagine you're a defender, right? And you're trying to ensure that the images that come in does not decrease the accuracy of your model, right? Because there could be a potential adversarial attack. Okay, so what should the defender do? Yeah. Now, in this case, the defender would be, in our work, we are thinking of the following. The defender would be thinking that perhaps there's going to be an adversary, an attacker, that is going to perturb the image. So if I know the kind of strategy that the attacker is using, for example, in our paper, we look at the use of parsimonious, right, which is one of the attack strategy, then how can I, as a defender, respond optimally in my defense strategy, all right? Now, at the same time, the attacker could also ask the same question. Now, if I know that there is going to be defender and the defender is adopting a certain strategy, then how would I respond in kind with my attack strategy so that I can improve my attack, right, of your model, okay? And you can imagine this to be some kind of chess game, right, where the attacker is thinking about what the defender is going to do. And the defender is also thinking about what the attacker is going to do. And you can see this recursive reasoning going on, right? And what we have shown in this work is that if you increase the recursive reasoning level, it's going to improve the performance of your attack strategy or your defense strategy, right? Uh, as compared to not exploiting recursive reasoning. Of course, there are certain assumptions that have to be made. For example, do we know what would be the strategy of the opponent? Now, of course, again, we ask the following question as well. Oh, but what if the opponent is going to know our strategy and therefore react accordingly? And that's where the recursive reasoning becomes useful. We have also tested against the case when what if the opponent reasons with a strategy that deviates from our knowledge, right? And yeah, we have also shown results for that as well. Okay. Now, interestingly, such a piece of work can also be applied to multi-agent reinforcement learning, where there are multiple agents with deep neural networks, right? And we are trying to optimize the parameters of their deep neural networks, right, for the purpose of RL. Okay. How are we doing on time? Let me see. Oops. Okay. Let me. Oops. Right. Maybe I'll take 5 more minutes to finish off. So in this Bayesian optimization technique, right? We are asking the following question: what if you know, the one that is able to gather the data or collect the data, right, or the data curator, it does not have the expertise to do optimization, and it needs to outsource its optimization task to another company, right? And as an example like this would be the hospital, right, setting. Now, in this case, you can imagine that this party with the data, right, or who can get hold of the data would want to privatize its data set so that the company that it outsourced to would not be able to peek into the raw data, right? And as a result, what we have done is that we applied differential privacy on the data itself. Now, of course, for those who knows differential privacy, you know that it amounts to adding noise to the data. And as a result, how is that going to influence the performance of the optimization? Now, in this work, this is the part where we are going to study, right, how differential privacy affects the optimization performance in Bayesian optimization in the context of the outsourced setting, all right? And you can see that this will be relevant to healthcare, finance, and real estate, all right? Now, last but not the least, this is a work in submission. It pertains to the notion of meta-learning or transfer learning, right? Now, in the event that I have some previous tasks, optimization tasks where I have already some data available, can I make use of those correlated tasks to help me to accelerate, right, the performance of my BO in this current task, right? Now, in this problem itself, it is kind of related to meta-learning, except that we're talking about optimization, all right? And what's interesting as well is that we look at the following notion. Typically in meta-learning or transfer learning, we kind of assume that, you know, all previous tasks that you, or where you have pre-trained something, they are always helpful, right, to your current task. But how sure are we that they are always helpful? Now, what if those tasks are not helpful, and in fact, it may hurt your learning or your optimization performance? And in this line of work, this is something that we cater to. We want to be robust, right, to tasks for which they may not be helpful to the current tasks, right? And as a result, we have this online learning mechanism that allows us to learn whether the previous tasks are correlated or not, whether they hurt or they help. All right. So some of these examples, right? For example, in human activity recognition, we're trying to train a model to do that, right? We can make use of pre-trained models from other individuals to very quickly bootstrap the model for another individual, right? Another aspect would be clinical diagnosis. We can imagine that for clinical diagnosis, there'll be new data coming in every week, right? And the hope is that we don't have to re-explore and ask ourselves what would be a better deep learning architecture when I have more data now. Now, the question is, can I make use of models that were trained in the previous weeks or days, right? To help us to train the model or figure out the neural network architecture that is optimal for the day that I have more data, right? As compared to the previous days, okay? Now, we can also apply it to a very simple like cut pull problem, right? On reinforcement learning, where we exploited previous data from previous tasks to help us to very quickly get the pole to be erect, right? Or to balance it well, right? Using just 15 iterations or 15 data samples, right? So yes, so these are some of the samples of what we have done with Bayesian optimization. And I've given a list here of where it can be useful, right? I've already shown you or mentioned quite a few about hyperparameter optimization in reinforcement learning and multi-agent reinforcement learning. Simulations folks are very excited about VO, right? Because they often take days to run a simulation and the results are bad. Material design as well. I do know in A*STAR, the Institute of Material, IMRI, right? They have been using Bayesian optimization widely, right? You can use it in active search. Recently, I have a project on growing crops, and as a result, I'm going to use that in precision agriculture. Very timely for this COVID situation, especially in Singapore, where we are hoping to be self-reliant, right, in terms of the food security. And last but not the least, I'm also involved in AI Singapore. We have this AI in the Health Grand Challenge. I've met clinicians where they are trying to do personalized drug therapy. You'd be surprised to learn that actually they have no, whatever drugs that they are, prescribing, it's not so clear that it is going to work in the same way for every individual. But how can we use Bayesian optimization to help us out, right? To very quickly get to a combination that works best for a patient. All right, that's all I have for this or our efforts in Bayesian optimization. Thank you.